Hello, I'm Doug Montgomery, and I would like to welcome you back to another one of our Design of Experiments Fireside Chats. And some of you may be relatively new to our Design of Experiments course on Coursera. So I'll tell you a little bit about the Fireside Chats. This is something that we do every month. I try to make sure that we have a really entertaining guest speaker. And we talk about different topics, some of which may be related to the course itself. Sometimes they explore new things that we haven't really spent a lot of time on in the course. And that'll be the case today. As I say, we do these monthly. We try to always make sure that there's time for questions at the end of the guest's presentation. Usually about a half an hour of time for questions. This is a great time for you to participate, and you can ask questions about either the course itself or things related to what the guest has talked about, and or even some specific question relating to a situation or an application that you're involved in. And if you're on Coursera, you'll find all these Fireside Chat recordings posted to the course. They'll be in the Resources tab of your Coursera course. A quick reminder about a couple of things. Please keep your microphones muted and your cameras off during the session. That'll keep the background noise down for everybody. And if you want to submit a question during the Fireside Chat, the best way to do that is with the chat function. So you don't need to wait until the Q&A session begins. You can start putting those questions in anytime that you'd like. If we don't get the questions answered completely during this course, during the Fireside Chat, then we'll try to respond to it later on, and those of you in Coursera will be able to see that. Okay, so let me introduce our guest today, Dr. Christopher J. Nachtsheim. Chris is the Frank A. Donaldson Chair of Operations Management in the Supply Chain and Operations Department of the Carlson School of Management at the University of Minnesota. He got his PhD at Minnesota in operations research in '79. He's the author of two major textbooks, Applied Linear Stats Models, the 5th edition, and Applied Linear Regression Models, 4th edition. Both of these are co-authored with John Nieder, Michael Kuttner, and William Lee, along with Brad Jones from SAS. And by the way, Brad has been a guest on our Fireside Chats, and he is going to be a guest on an upcoming Fireside Chat. I've got him coming back again. But these two guys developed a technique called definitive screening designs. Very powerful idea. We talk about those in the course. He's also, along with one of his PhD students, the developer and inventor of the coordinate exchange algorithm that is the most widely used method for constructing exact optimal designs. He's published extensively in the statistics literature. He's been an examiner for the Malcolm Baldrige National Quality Award. He is a 4-time recipient of the Brumbaugh Award of the ASQ for the best paper published in the area of industrial quality control. He's a 2-time recipient of the Nelson Award from ASQ for the published paper having the greatest impact on practitioners. And he's a 3-time winner of the Jack Uden Prize for the best expository paper published in technometrics. And the topic that he's going to talk about today is based on 2 of those technometrics papers, both of which won the Uden Prize. He's also a recipient of the 1992 ASME CAE CAD-CAM National Best Paper Award. He's a fellow of the American Statistical Association. I have known Chris a long time. Maybe he'll remind me of this, but I believe the first time I met him was when he was a PhD student at the University of Minnesota. And that, as you can see, was a long time ago. That was back in the late 1970s. And so I've known him a long time and greatly respect his work. And his daughter actually came to school here for a while. I had the pleasure of teaching his daughter Abigail in a few classes. So that's my introduction for Chris, and I'm going to turn the show over to him.
Thank you, Doug. And welcome everyone to this fireside chat. I'll never forget when I was a grad student a few years back in the late 70s. And I was a student in the industrial engineering operations research area at Minnesota. And we were just an area, we weren't a department, and we wanted to form a department. And our best chance of being able to form a department was to hire this already famous guy named Doug Montgomery. And he came and interviewed, and I met him, and I thought, wow, this is a really famous person. And of course, he was so famous, we weren't able to hire him. He had better options elsewhere, I guess.
Well, the winter was a factor.
What's that? The winter was a factor. Yeah, I think you came in the middle of winter.
That's right. I was dying.
Yeah, that wasn't a bright move on our part. But anyway, I've known Doug forever since then. We've done a lot of things together. So I guess I'll launch off here, and I should share my screen. Let's see. I think this, or desktop, I want to do the, oh, we could do the PowerPoint, I guess. Does that work?
Looks good to me. Okay.
So I want to talk about design experiments for engineering dimensional analysis and kind of give a simple introduction to this idea. I'm going to give you some of the basic ideas of dimensional analysis. So when I use DA, I'm talking about dimensional analysis. Some examples, and then a glimpse at how we design experiments for these special kinds of cases. I want to tell a story at the end how I got involved in this problem, and then we'll get off into discussion, Q&A. Doug can take back over. So these are collaborators in the work that I've done in this area. Mark and Tom Albrecht are two of the best master's students I have ever had in my life. Well, they are the two best master's students I've had. And then Dennis Cook, very famous statistician, still at the University of Minnesota, was actually my thesis advisor. So I want to start off by just talking about a difference in approaches in a problem between how an engineer might approach a problem and a statistician. Let's take a really simple problem. We want to characterize the effects of two variables. So these are our factors, velocity and time, that's x1 and x2, on the response variable distance. So how do velocity and time affect distance? Now we're ignorant, but an oracle knows that the true relationship is distance is velocity times time. And maybe there'll be some measurement error thrown in as well. So how do we figure this out? How would we figure this relationship out if we didn't have a physics book? Well, a statistician would say, let's use DOE. We got two factors we can vary, and we're concerned about curvatures and interactions. So we might run what's called a central composite response surface design. Doug, have you had a chance to talk about that yet? Just curious.
They are, CCDs are covered in the course. We have a whole course module, basically, that talks
okay.
about
Later on, that's all right. Very widely used kind of experimental design. Now, after we run the experiment, we get the data, we fit the model, we fit a quadratic model. So you can see we've got the linear effects, beta 1, x1, and beta 2, x2, plus the interaction between the two factors, beta 1, 2, x1, x2, plus curvature terms, beta 1, 1, x1 squared, and beta 2, 2, x2 squared. So that's our regression model after we're through with the experiment. We fit the model, and then we'll drop out the insignificant terms. Well, when we run this model, the beta 1, well, all of those terms will drop out because they're not relevant. They're not part of the true model. The true model is E of y is beta 1, 2, x1, x2. So we get our prediction equation, y hat 1.04 x1, x2, which is approximately velocity times time. And we have discovered the truth here. And that's what we do as statisticians. Now, the engineers take a different approach to problems like this often. So we say the engineer thinks more like Isaac Newton and worries about the mechanics of the physical systems. And these things are governed by physical laws, and they worry about dimensional homogeneity. A physical equation must be dimensionally homogeneous, which just means the units on the left side of the equation, distance, which is miles, should be the same as the units on the right side of the equation. That should also be in miles. Now, we think it's a function of v and t. The h is the function, we don't know what it is, but we think it's a function of those two factors. So what would the engineer do? Well, we have the units. So distance is in miles, velocity is miles per hour, time is in hours. And I learned when I got into this that when engineers put square brackets around a variable, like I've shown up there, that just means the units of. So units of distance is miles. And the engineer may look at this and say one-dimensionally homogeneous possibility is distance is equal to a constant times velocity times time, because the units are the same on both sides of that equation. So one final simplification, we'll divide both sides of the equation by VT, and we get this equation, d over VT equals a constant. And we're going to try to figure out what that constant is. That's like beta naught in our regression. The beauty of d over VT is it's miles over miles, and so they cancel, and it's dimensionless. So turns out that to estimate the constant, all we need to do is pick a velocity, pick a time, run the experiment, observe the resulting distance, and plug in. And we can find C. We can replicate that if we're worried about experimental error. So that's a very different approach. So let's kind of summarize here. First, there's the statistician's approach. There are two factors to vary in the experiment. The model, there are 6 parameters in our regression model. Now, how valid is this model? Well, the model is valid, as I'm sure you've learned, inside the experimental range of factors. Extrapolation is very, very dangerous with regression models. And what is the explanatory power of the model? Well, we've got a local empirical model, and it's got good explanatory power locally. Let's look at the engineer's approach. How many factors are there to vary in the experiment? Turns out there are no factors to vary in the experiment, 0. There's just one fixed constant C. The model parameters, again, just one fixed constant. Scalability. Now, here's the thing that was shocking to me when I got into this. This model will scale over any experimental range. In other words, you can extrapolate all you want with this model, and I will talk about that a little more coming up. And the explanatory power, we don't have an empirical model. We can result in a universal law, kind of an analytical model for how distance varies with time and velocity. So there's a lot of power in the engineer's approach. Just to summarize, we have dimension reduction. The number of factors was reduced by the number of measurement dimensions in the variables. We had distance and time. And so the number of factors, we started off with 2, but it gets reduced by 2, so we have 0. So we have fewer factors to run an experiment on, and we can save some money that way. Another one, the big one, I think, is scalability. The empirical models are valid within the range of the factors. That's the statistician's approach. But the dimensionless models can scale to any size, which is very, very powerful. Why is that important? Well, suppose you were trying to optimize a turbine. You're trying to build a turbine and you'd like to run experiments with it. Well, you can't run experiments with turbines of this size. It's just too expensive. Can you imagine? Let's build 16 turbines this size and test them out. I don't think so. However, you can do all kinds of experiments with turbines of this size. And so you can build your model running these little sort of toys. Looks like it's been printed. And then you can extrapolate to the larger sizes. Amazing. And there's I'm going to give you another example of extrapolation, which I think is even more compelling. I'm going to run a little film. I'm going to run a little video here.
On the evening,
Can you hear that?
August 5th, 2012 Pacific Daylight Time, NASA's Mars rover, named Curiosity, entered Mars' atmosphere at 20,000 kilometers per hour. Drag slowed it down to around 1,600 kilometers per hour, at which point a parachute opened. This parachute slowed the rover more to about 320 kilometers per hour, or 90 meters per second. Finally, after rockets decelerated it completely, the rover was lowered to the surface of Mars. Every step of this dance was carefully choreographed and rehearsed in many experiments here on Earth. But how could NASA engineers be sure that their designs would work on a totally different planet? The answer is a problem-solving method called dimensional analysis.
So I want to talk about this example, this Mars rover DA process. We start like we're trying to build a regression model, and the engineers will say, well, the velocity of the rover will be a function of dm, g, and rho, the diameter of the parachute, right? The bigger the parachute, the more it's going to slow. The mass of the rover, how heavy is that guy? The gravitational constant, and the density of the atmosphere. So we have a model. We think those are the factors that are going to affect velocity, but we don't know what F is. F is this unknown function of these four factors. Now, over on the right side, I wrote down the dimensions of each of those factors in our experiment. And we have, you can see we've got L over T for velocity, et cetera, length, mass, L over T squared, and M over L cubed, mass over L cubed. Anyway, we have three dimensions, 3 units. We get length, time, and mass involved in our factors. The reason that's important is I think we're going to be able to reduce the dimensionality of this problem by 3. So, what's going on here? There we go. So now how do we get the DA model, and what is the DA model? Well, there's a little step-by-step process that you use to come up with the DA model. At each step, one variable is used to eliminate the dimension M, L, or T from the set of variables. And at termination, we're down to dimensionless variables. So here we go. I'm just going to do this kind of quickly. This is all in one of the papers we wrote, and it's in engineering books and so forth. But here's where we start. We've got the response variable velocity and the 4 factors and their dimensions. So at step 1, we want to eliminate a dimension. So we're going to use D, which is length, and we're going to eliminate it. So in that second row, the result will be length is gone. Okay, now to get rid of length for the velocity, we'll just divide by D. We'll take V over D, and that'll cancel out L, and the dimension will be time T inverse. There's no length involved in mass, so that will stay the same. On the gravitational constant, it's L over T squared, so Again, we'll divide by D to get rid of L in that. And so the resulting units will be T to the minus 2. And for rho, we've got ML to the minus 3. So we can multiply by D cubed, and that will give us units which are just mass. That's step 1. Every step now we're going to eliminate a variable. So next we'll choose to eliminate mass, the second variable. So we have a blank line over on the right side where mass was. We can't do anything with the first row, but the last row we can divide by M, and that will be, the result will be unitless. Now we're down to one variable left, this GD inverse, which is of units T to the minus 2. And so we'll remove T from step 2 using that, GD to the minus 1. And since VD inverse, that's our response variable, is of units T to the minus 1, we're going to use the square root of GD inverse, because that's T to the minus 2. And we're going to multiply that out and get it to be dimensionless. If you didn't follow that, that's okay. It's just algebra. In the end, we wind up with two dimensionless variables. The one is V over square root of DG. That's the response. And rho D cubed M inverse is the one factor. So here's our DA model. V over the square root of DG is some function of one factor, rho D cubed over M. And we rename those using the pi group terminology. So pi naught is the response, is equal to some function of pi 1. And so I've got a one-dimensional design problem. I just have to vary pi 1, record the response V over the square root of DG, and then we can model the response. This summarizes everything. So now, the objective here is to estimate the function by varying that single factor pi 1. I mean, is it a quadratic function? Is it linear? Is it increasing? Is it decreasing? That's what we're going to do with the experiment. Here's the problem. On Earth, we cannot vary rho, which is the density of the atmosphere. We want this to work on Mars. So I can't change the density of the atmosphere if we're going to run this experiment on Earth. So rho is fixed. We could vary mass, M, the mass of the rover, but that would be pretty expensive. So we don't need to. The only thing we need to vary is D. That's the diameter of the parachute. That just says make a bunch of parachutes of different diameters, test them out. And then we can, we get our answer. So here is the logged earthbound results that the people from MIT published as part of their video. And what we're seeing is, what I'm publishing here, what I'm showing here is the log of the pi groups. So on the y-axis, we have the log of the response, pi naught. And on the x-axis, we have the log of pi 1, which is our factor. And we could probably fit a quadratic to that if we wanted. Okay, but that's describing what's happening on Earth. But what about Mars? Well, all we have to do is change the gravitational constant to Mars gravitational constant and the atmospheric density to Mars density and recompute the pi groups. And we get a new plot. And this is what would happen on Mars. It's pretty amazing. So I solved that equation for velocity. And then I fit a smooth to it. And we wanted to know what would be the diameter of the parachute that would get us would slow us down to 90 meters per second. And the answer is 101 meters, according to the model. Okay, so the example, this is the power of D, shows not only can we extrapolate outside the range of the experimental region, we can change physical constants without actually changing them. And we can see the effects of changing physical constants without changing them. So run an experiment on Earth and extrapolate it to Mars. Pretty amazing. How do we know this process works? Well, there's this thing called the Buckingham pi theorem, which was proven in 1914, which says basically this process works. And it was first proven in 1878 in the context of electrodynamics. That's a very famous theorem. All right. So you've seen how we've reduced the dimension. We've got these pi groups now. Pi naught is the response. Pi 1 is a factor. Maybe we have pi 2 as a factor. And I want to talk a little bit now about how do we design the experiment. So this is a simple example taken out of White's fluid mechanics book. Pump design. The outputs are head pressure and brake horsepower. And the predictors are Q, discharge, D, impeller diameter, N is shaft speed, rho is fluid density, mu is viscosity, and epsilon, which we're going to leave out, is surface roughness. The engineers could leave that out because they were only going to use one surface. They weren't going to experiment with that. We actually had 2 responses, but that's not relevant here. It doesn't matter. We have 2, we started with 5 factors and we had 3 dimension units. And so we wind up with a dimension reduction of 3, which gives us 2 factors. And so we could use that Ipsen approach to get the DA model, but here it is. So only Q, N, and D are varied. Mu and rho are going to be held constant. All right, so if I'm going to change 3 factors, that's kind of like a 3-factor experiment. What are the ranges? Well, we got that from the book. Here are the ranges of Q, N, and D. 4 is less than or equal to Q is less than or equal to 30, 710 to 1170 for N, and 28 to 42 for D. Now, that's the design space in those original factors. But what I need to know is what is the design space in the pi groups? I'm not changing those factors per se. I want to change the pi values in my experiment. Those are the real factors now. And just to recall, pi 1, the first factor, is Q over ND cubed, and pi 2 is ND squared, where the Q and the N and the D fall into that rectangular hypercube region in up above, a little 3-dimensional cube. So here's a picture. What we're used to in designed experiments is the picture on the left, where we have 3 factors, Q, D, and N, and I want to explore that space. So I might just look at the corners. I might use a response surface design where I look at values in the centers of the faces and so forth. Unfortunately, that's not what we're interested in. Now, if I take any value in chi, any combination of N, Q, and D, it gets mapped over into this kind of weird looking purple region in the pi 1, pi 2 space. So that's the design space that we're really interested in. We want to spread pi 1 and 2 pi points out in that purple region to get a good, powerful design to estimate the function. Is it a quadratic again? Is it a cubic? What is it? So that's the situation. So there are these two design spaces I really want you to remember. One is the design space in the original variables, but that's not what we're really interested in. We're interested in the design space in the pi groups. So, oh, by the way, if you take a log of all the points in the pi space, you get a parallelotope. That's a fun fact that we used in one of the papers, because if you want to know if a point is feasible or not, you can look to see. It's easy. There are easy routines around for telling you whether you're in a parallelotope or not. You can just forget that for now. I just wanted to show that. Okay, so how do we design? What we've recommended are non-parametric designs. These might be just uniform designs or minimax distance designs. I'll show you a picture in a minute. Or kind of standard parametric designs. You might use a d-optimal design for a third order or higher order polynomial. We suggested I-optimal or L-bar optimal designs as alternatives. I'll show you what I mean by that. So here's how we do this. Back in that original space where we've got all possible values of n, q, and d, and each combination maps into the pi space, we can search around in the cube. Well, I'm sorry. As we create our design, we'll search in the cube space. We will then transform the point over into the pi space and see if that's a good point to include in our design. And then we'll search throughout that cubic region to find the very best points when they have been transferred over to the pi region. So what I recommend is that we use the coordinate exchange on the chi space. Every point is transformed into the chi pi space, and we use that to evaluate the optimality of the design. This is an I-optimal design that I constructed for this example. This is for a cubic polynomial, could be for linear, quadratic, or cubic. And you can see that those points are really nicely spread out inside of that strange region, which is the pi space. So that's the optimal design, one optimal design. You could also construct a non-parametric design. And you probably haven't heard about computer experiments or non-parametric experiments yet, but that just means we want to spread points out uniformly throughout the space. And one way to do that is just generate random points in that purple design space. So one way to do that is to put a square, if you will, or a rectangle around that encompasses the purple region, and you can generate uniform points on that two-dimensional square and then just drop points that are not inside the purple region. You could also use fast flexible filling if you're using jump. Okay, so that's a kind of an overview. I want to just review key points here, and then I'm going to tell a story. So DA is a powerful tool for modeling physical systems. It leads to scalability. You can extrapolate to your heart's content, and it leads to dimension reduction. Parsimony, which is always nice. Fewer factors to have to experiment with. Creating the DA model is pretty easy if you're working with a scientist or engineer who gets it. I mean, this is a case where statisticians and people designing experiments have to work closely with the subject matter experts. And then I gave you a little bit of a feel for how we can create designs.
Chris, I don't mean to interrupt you, but this looks like a great space, a great place for various types of space filling designs. And we do talk about.
Oh, you do? Yeah.
We talk about computer experiments in the course. And, Latin hypercubes, we talk about those and other kinds of space filling designs. It just seems like this is a perfect application for that.
It is, Doug, and we recommend that approach. On the other hand, I love this design.
Yeah.
Which is a parametric design, and it gets us out to the edges, and that may give us more information. But they're both absolutely appropriate. Yeah, good point. So I'm going to tell this little story about how did I get involved? I'm not an engineer. How did I get involved in dimensional analysis? And I want to go back to my first job was at Los Alamos National Laboratory back around 1980. And a engineer came into my office and said, I want to design this experiment. And he said, and I have these 2 pi groups, and I want to run an experiment on the pi groups. And the pi groups, each was a function of 3 of these original factors, just like in my example. And I said, you can't do that. You can't, you're changing all of those factors in the pi group simultaneously. You can't understand the effects of the variables in the pi group. You have to do it by changing the original variables. In other words, I told them, don't work in the pi space. You need to work over here in this 3-dimensional cube, which is what we're taught in designed experiments. I gave this guy very bad advice. I was completely wrong. And, but, you know, I was the statistician. He did what I told him, which was really unfortunate. Fortunately, I got out of Los Alamos without being fired. Anyway. So then, you know, I about 8 years later, I was a professor at the Carlson School of Management. I gave a talk on design of experiments, and one of the professors in our group was a mechanical engineer by background. He later went back, got a PhD in operations management. And he said, what are you doing? Why are you using those variables? Why aren't you using the pi groups? And I went, uh-oh, uh-oh, this has come up before in my life. So I sat down with him, and he took me to his engineering book, and he showed me the chapter on dimensional analysis. And I thought, well, I can't really do anything without somebody to work with. So I kind of forgot about it again. And then in 2011, I was working with Mark Albrecht, was my master's student, and his brother was an engineer at Boston Scientific. And he had run an experiment with 2 or 3 factors, standard experiment, and he fit the model, and he got 90% R squared. And then he looked at it and he went, I can combine these 3 factors into a pi group. I'm going to do that, get it down to 1 factor, and then just run a 1-dimensional regression. And he got a higher R squared. And he thought, what's going on here? So he called his brother Mark to say, I understand this. I used a pi group and I got a better prediction model than using these 3 factors in this very complicated model. And so Mark and I said, we need to go visit your brother. And we went over and he showed us his results. And then suddenly I remembered all this stuff from 1980 and 1988. And so I said to Mark, for your master's paper, look into design of experiments for dimensional analysis. And he did, and there was nothing in the literature. Nothing. No one had ever even thought about it. And so he wrote his master's paper, and that wound up getting published in Technometrics. And then in 2014, Dennis Cook and I were giving a PhD seminar, and one of our students said, I'm interested in this from a multivariate perspective when we have more than one response. And he proved a version of the Buckingham pi theorem for the multivariate case, and that led to a second paper in this. So that's my presentation. And I'm willing and happy to answer questions and turn it back over to Doug.
Chris, thank you very much. This is really, to me, fascinating material. I've heard you talk about this before, and I've read your papers in Technometrics on this, and I've always found this to be a really innovative idea. I've never run into a situation of my own where you could use this, but I've always figured that if I did, you were going to be on speed dial, and I would call you up and try to get you involved. Have you done any other applications of this since the published work?
Well, not since the second paper, but there's some other applications in that one. Now, by the way, I wanted to tell you, Stu Hunter, of course, is a good friend of yours.
Sure, and yours too.
And mine too. And when I gave that paper the original paper, I was giving the talk at the conference, and Stu's who's a bit older than we are. He's 95 now, I think, or 96. He said,
actually, he's going to be 100 years old.
okay. No.
On June the 3rd, and I'm going to be 80 on June the 5th.
Well, you're amazing, but you're not as amazing as Stu yet.
Oh,
Anyway,
nobody is.
anyway, he said, you know, Chris, I thought about this back in about 1942. He said, but I never pursued it. And he said, I wish I would have pursued it. So, you know, it's just, I think the big lesson I got out of this was statisticians need to listen to the people who are designing the experiment and don't necessarily impose your will on your client. The client may know better.
Yeah.
Anyway.
Yeah, that in fact is a very good lesson for everybody. Is good. In fact, I talk about this in my own experimental design class. Is that good experimental design is a result of collaborative work. The last thing you want is to have a person who is the expert go away and sit in a closet someplace and design the experiment, because invariably they will do something that probably isn't the best. In fact, I've seen cases where the expert has designed a very narrow experiment that is been set up to prove that what he thinks is the answer is in fact the answer. and you know, collaboration is the key to success in a lot of experimental work.
Well, it really is. And you've written about that. It's in your book and you've written papers on that. And it's really, communication is very important.
It is. And I've always thought this was a great example of how people with a really deep understanding of the subject matter can interact with those of us that know some things about design of experiments and get a really great result. And I've always considered this work to be really groundbreaking work in the area of experimental design. I just sort of wish it was more widely known in the literature. And in fact, I'm thinking maybe the next time I revise my experimental design book, I'm gonna stick some material in there on this dimensional problem.
And Brad Jones has talked about putting this capability inside of JUMP. I assume you folks are using JUMP.
Yeah, we use JUMP in the course, and in fact, we actually have in the Coursera course, we actually have video clips that show you how to take virtually every example in my textbook and set it up in JUMP and run it.
Nice.
And so people that going through the course can get sort of a nice tutorial, if you will, on how to use JUMP.
Wonderful.
Any questions?
Yeah.
Have we had anything come in? I guess we've not had anything come in from our participant group, but I did want to ask you something, and what are you working on right now? I know that you and Brad have been up to some things, and I'm curious about what you're up to right now.
Couple of things. One is in effect, we're extending definitive screening designs to more applications where there are mixed levels. Definitive screening designs were originally set up when we said that all the factors had to be continuous so that you could have a low, a medium, and a high. And then as you know, because you were the editor, we published a paper which showed how you could incorporate categorical factors.
2 levels, yeah.
2 levels. And we're looking at ways of extending that work by, it turns out, these definitive screening designs are a fold over. And it turns out that if you fold it over and then fold it over again, the definitive screening design, and then add some two-level kind of factors in using Hadamard matrices, you can get some really beautiful results. So you're kind of combining those factors optimally.
So you can take the fold over on the two-level factors and convert that into something other than two levels.
That's right.
Yeah.
Yeah. And the other thing I've been working on is, and by the way, this was inspired by Tom Albrecht. I have a PhD student who is working on machine learning and fitting those deep learning models. There's lots and lots of parameters in those models that you have to set. And what is the best setting of those parameters? For example, how many in a neural network you might have different numbers of layers. I mean, you might have a 1-layer neural network. You might have a 10-layer neural network. There's an optimal number of layers to get the best model. And how do you find that out? Well, you run experiments, computer experiments.
Yeah.
And so we've been looking at design of experiments for, optimizing machine learning. That's with, and I know you briefly met. I know you met my student, Gautam Sunder.
Yeah.
And so there's another amazing application of design of experiments. It's, Doug,
Yeah, I've done some work on that myself.
oh, yes, you have. We referenced your paper.
Yeah, with some people that are now at Intel, and it was a kind of a novel application for me. I was really quite pleased that with the results we got too. So I think it is a great interface between experimental design and all of these folks that do all this data mining, machine learning types of stuff.
One of the things I've learned is that experimental design is exploding again.
Sure.
Because of all of the online experimentation, A/B
Right.
testing, and all of this kind of work with machine learning and so forth. My colleague, my student, Tom Albrecht, was working at Boston Scientific when he got us interested in these problems, but now he's with a company called Atlassian, and he's still doing machine learning. I don't know the company Atlassian. I think they're kind of a marketing company. They're based in Australia. So I don't think you and I would know of them, but they have a design of experiments department.
Yeah.
Made up of nothing but people who know how to run designed experiments because they're doing it all the time. It's just amazing.
Two of my relatively recent PhD students, when they finished, they went to work for American Express, and they worked in a group similar to what you're describing. That's all they did, is that they designed experiments for Amex applications, most of which were this A/B testing type of stuff. And they were looking at a wide variety of different kinds of applications of this and getting into some fairly complex experiments, factorial type structures and,
Nice.
doing some really interesting things. Both of them ended up leaving Amex because they got a better deal.
Oh, yeah, sure.
Someplace else, but they were doing some really, I thought really interesting work. And in fact, one of them, his name is Edgar Hassler. Edgar has actually been a guest on the Fireside Chats, and he actually talked about A/B testing, which is again not something that we really talk about in gory detail in the course, in the Coursera course, but he gave a very nice introduction to what A/B testing is all about, and some of the methods and some of the the pitfalls and perils that you run into in doing this. But
you do talk about it, Doug, in its simplest form. It's just a one-factor experiment with two levels.
That's right. It's a two-sample t-test.
It's all it is. And do you want to use Is design 1 for the website more effective than design 2? Let's test that by taking random samples of users. Of course, it's more complicated than that because
Yeah,
you may be looking at millions of observations, and they're all
and there's some issues about the random sampling part
that's right.
of that too. That's another another very big concern because as I've often told my students, without random samples, statistics doesn't work. You know,
That's right.
It just becomes arithmetic. It doesn't necessarily lead to cause and effect. But the one thing I am glad to see is that there's starting to be more interface between the machine learning and data mining people and experimental design.
Yes.
Because I've argued for years that data mining doesn't really establish cause and effect. All it really does is enable you to generate hypotheses. And then you have to come up with a clever way to actually test those hypotheses with some sort of designed experiment. And that's a challenge. But that's how you really, that's how I think you take advantage or utilize the power of data mining techniques is to integrate them with some sort of systematic experimental design.
Oh, I couldn't agree more. And predictive modeling can be, I don't care how much data you have, predictive modeling could be a disaster. Once you start assuming cause and effect in your model, the cause and effect may be exactly in the opposite direction.
Yeah.
In a lot of those models. But of course, people assume it's cause and effect. And then you get into trouble.
Oh yeah, and I tell a story on myself, which you may find humorous, okay, but it goes back to my days at Georgia Tech as a faculty member, and I had a colleague, a very good friend, who was an engineering professor in another department, and he was doing some consulting work for people up in North Georgia that make well, I'm just going to refer to it as goop. Okay, and this goop forms the backing for indoor-outdoor carpeting. Okay, and so he's a chemical engineer, and he says these guys that make this goop are asking me a lot of questions about how to make this process work better, and he said I don't know that I'm the best guy to help them. So would you get involved? So yeah, I go up and talk to the guys in the goop factory, and start looking at their process. And sure enough, they have several process variables that they could vary. They've never characterized this process. And I said, well, you know, we probably need to think about doing something to characterize and then optimize this process. And so I got them thinking about doing a screening experiment, and then maybe you know, something like a response surface experiment, and you know, and the guy who was the chemical engineer, he kind of had heard of that, so he thought that was a great idea. So the engineering team is all set to do this. They are really excited. And they said the only thing now is we have to ask permission of the production and operations guys to actually run this experiment. So they did. And the production and operations manager said, so as I understand it, you're running this experiment just to collect data. Okay. And they sort of naively said, well, yeah, we're going to collect data. He says, you know, back in the engineering area, there are all these file cabinets, and these file cabinets are full of data on every batch of this stuff that we've ever made since time immemorial. And it says, so instead of running this experiment, which is going to tie up my plant for 3 or 4 days, take the data in the file cabinet and do something with that. So, you know, I got the data, and I took it back to Atlanta, and I bought myself some time on the Georgia Tech computer and loaded all of this bloody data up and started doing regression models. Okay. And I fit all sorts of regression models. And so after a couple of weeks of you know, playing around with this, we went back up to see the guys at the plant. And I said, okay, when you analyze the file cabinet data, here's some things that really sort of jump out at you. This variable, that variable, they seem to have some real effects. And you could see the engineering guys shaking their heads. Yeah, they sort of thought that made sense. And I said, now here's this other variable, temperature T1, you call it, has no effect at all. And the engineering guys started laughing, and when the engineers laugh at your solution, you're
in trouble.
You're in trouble. And I said, okay, guys, what's wrong? And they said, well, this can't be right. We know T1 is important. That's why we control it so closely in the process. Yeah.
You don't change it.
They actually had a PID controller on this thing. It never moved, or it didn't move very much. And it reminded me of something I learned long ago when I was an undergraduate student doing summer engineering jobs at Union Carbide up in West Virginia. My manager up there, who was the plant manager, he once told me, he said, Dougie, in order to find out what happens in this process when you change a variable, you actually have to change the variable. That's about the smartest advice that any of us can remember.
Exactly.
Yeah. And that example that I just described, where I made this stupid mistake, just highlights the problem with uncontrolled data mining.
Oh, it really does. It really does.
In many cases, the important stuff never changes enough for you to really see it. Yeah, that's true. Well, this has been a fascinating topic, and are you doing any more with this topic? Have you got any more research students interested in this?
Well, not currently. There are other people working on this.
Okay.
Dennis Land and other people have students working on this kind of thing. It's become a pretty active area of research. But no, I'm busy with what I've got right now.
Well, you always seem to be staying busy, so.
And out of trouble.
Well, that's the key.
Yeah, that's the key.
Well, I think we're getting close to the end here. We've got another minute or two to go. I don't know that we've had any more questions arise. So, once again, I want to thank you for showing up for this. And it's too bad you're not here. I thought you were actually going to be here when we were settling on dates, but
coming in on Saturday.
Okay. Well, are you going to be here in the spring?
I'll be here in the spring. Absolutely.
Okay. Well, maybe we can get you back for another appearance in the spring, because I know you've got a lot of fascinating things that would be fun to have you talk about. So we'll try to get you back for another guest shot.
I would love that, and thank you so much for inviting me. It's been a real fun thing, and I always like talking about DOE.
Would you be willing to share the slides?
Sure.
In your talk? I'd like to have them, and because I found this really kind of fascinating, and I have heard you talk about this before, but I don't have a presentation, so I'd just like to be able to take those slides and look at them. And when I revise the design book again, I may try to put something in the book on this kind of experimentation, and might ask you for a little bit of advice about how to do that.
Sure, that'd be fun.
Good. Okay, I think we're done. I think we can wrap it up, and thank all of our Fireside Chat participants, and hope you'll not only check out the video on this, but the recording, but check out some of the other recordings that we've had. And our next Fireside Chat is going to be coming up in early November.